Welcome back. Let's get started. Let's quickly review what we have done today, because we're finishing the random discrete random variable, and then we will continue on the continuous random variable. There's not much Excel to be done for this topic because they are much more like theory, and also this is why the homework to be assigned after we finish the continuous random variable will be focused on calculation. Okay, so there will be more kind of computational numerical exercise. So before we start, can you see my screen, or can you hear me, or can you see the screen? Yes, that's good. So let's very quickly review what we have done last week, because I think it has been quite a while after the break. I hope you have a nice Mid-Autumn Festival, have enough mooncake, but not too much. So very quickly, we go over what is random variable. Random variable, in fact, it's mapping outcome to number. In the other word, it's just assigning number to outcomes. Okay, because the sample space can be very large and many outcomes. So to simplify it, we put numbers to outcome. So that's the idea, right? Because say head or tail is no number, but we can say number of head, number of tails, right? So that's why when we toast 2 times or 100 times, then the sample space is still very simple, right? Because if you have record the history, then you'll be 2 to the power 100, then can be a huge set. But if you just record some number of head or tail, then just one single number is it from 0 to 100, right? So, and also it's very natural actually in the real world. We always measure, right? We always record what happened in the real world, right? When we're measuring like temperature or stock market indices, already we have measurement, we already collapsing what we have seen into numbers. Okay, so that's why already very naturally we have random variable. I hope that makes sense. Please feel free to ask questions, because we're just reviewing for the first 5 minutes. So discrete random variable, that is a discrete random variable. We can describe it through 2 things, which is called probability mass function or probability distribution function, right? It's just like the probability x equal to the value x. Okay, just remind you that the capital letter X is the random variable. Okay, the small letter x is the value, particular value, some constant. Okay. The next one is the cumulative probability function, which says what is the probability less than that particular number. Okay, so that is the idea behind. Okay, need to recharge my tablet. So, so we can have example of long and fair die. You can draw the probability function and also the cumulative distribution function. Okay, and then we learn the expectation, right? Which is a weighted average. Okay, it's a weighted average in the way that you're weighting each outcome by the probability, right? So it's a weighted average, but the weighting is a probability. Okay, you just and the variance, the same idea, right? It's just like the variance is the weighted average of the square difference from mean, right? So it's again the same thing. We know how to calculate them, right? When they're equally likely, then it's very similar to what we have in the first topics, right? And we know the expectation, the linear property of expectation, right? And also the variance property, okay? And then we do the portfolio, okay? And last class, we covered the uniform, binomial, and binomial. Okay, just very quickly go over that again. Uniform is everywhere equally likely, so it's 1 over n. Okay, and we know already this is, I think I don't need to go over that, but this binomial is a little bit trickier. Okay, just to repeat again, it's a outcome. Okay, you only have 2 outcomes. Either you have success or your failure. Okay, that is the only 2 things in the sample space. Only 2 things: success or failure. Success have probability p, and failure have probability 1 minus p. Okay, because they are mutually exclusive. Okay, and we denote number of success. Okay, or number of failure doesn't really matter, but as a convention, we record number of success as x equal to 1 is success, x equal to 0 is failure, right? Because it's number of success. Okay, and the probability function, right? Because success p, failure is 1 minus p, right? So that's why it's a very interesting way to combine these two is to use the index, right? P to the power x, 1 minus p raised to the power 1 minus x, okay? And here we prove, it's easy to show, how to calculate the mean is p, the variance p, 1 minus p. Okay, that is something I think we have shown. And then the last class at the end, we prove what is the extension of the binomial, which is binomial, right? Binomial is a trial, only either success or fail, right? And binomial is repeating this independence n time, okay? It's independent. What means independent is the previous outcome doesn't affect the next outcome, right? And is a number of success, okay? So if the value can be x can be equal to 0 up to n, right? Because you can have no success, have 1 success up to n success, okay? So there's n plus 1 outcome. And by combinatorics, okay, we explained already why is NCX, because the different way you can get success, right? You can have first success or last success, they are symmetry, right? So that's why by the you can have x success, then you can take n of x objects. So that's why we have NCX there. And we prove why the mean is NP and variance NP times 1 minus P, okay? And if you don't really care the proof, right, but we can use a shortcut because X is the summing up all the binomial trial, right? I think we talk about that, right? Because of the fact that a binomial NP, right, can be written as X of a binomial trial, right? There are n of them, right? And the expectation of each of these, right, binomial is P, right? So that's why X of binomial, right, is NP, right? The same idea applied to show the variance NP times 1 minus P. Of course, you can prove it, right, by the way that we have shown you in the very last set of slides. Okay, so someone asked me repeatedly worry about the complexity of proof. As I explained again, the proof will very unlikely, I would say probably no, but I cannot preclude it at the moment because I haven't made the test yet, but very unlikely that you appear in the test. Mainly will be appear in the assignment. Okay, maybe appear in some way in the assignment, but it will be very, 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 very unlikely that will be in the test. But I cannot preclude what is known because I haven't made the test yet, but I don't have any intention to make them appear in the test. But the reason why we have that is we should know why some result is true. Okay, we need to understand why they're true and what they're meaning. But of course, we not need to reproduce it, but need to at least know in principle how they are being arrived, right? Because you're given the result, right? You have to know why this is true, right? You may not fully follow it, but at least you know how, in principle, how we get there. Okay, so that is the idea, right? Otherwise, we just give you a bunch of formula, then we're done, right? But we need to understand what's going on there. Do midterm exam? No, we don't. But if you want, we can make one. But I guess you don't, right? Does anyone have any strong intention we have midterm? But I guess we don't, because it's very difficult to arrange the one in during the this online phase, because it's very difficult to how can I say, very difficult to protect the exam. Does it make sense? We don't have a midterm. So that's why instead we have a project component to be there. Okay, so make sure you learn something, but you'll be given homework after this this topic, so you can train yourself if you really. But we really need to train about this part. You need some work on some problems, just simple math, because this part is this set of slides about random variable and probability are more or less like some mathematical knowledge. So that's why it's difficult to avoid some exercise. Yeah, you need some routine thing. Any further question? If no question, we proceed to Poisson. Any question? If no, then we go to talk about Poisson. Okay. So Poisson is rather, I would say, it's rather common, and later you will see Poisson indeed is related to binomial. Okay, that's somewhat related to the idea that binomials with a binomial. Poisson is a special case of binomial, in the sense that of a rare event. What rare event means when n is big and p is small. Okay, so that is a very interesting thing, and usually using binomial to model something called counting. Okay, say how many consumers are coming to a coffee shop, it's a counting. A rare event like how many, say yesterday with a very big rain, right? So was number of events that occur during a year can model by Poisson. Okay, Poisson is something we'll be using to count the numbers. Okay, counting, and it's a rare event. Okay, so counting a rare event. There are many motivations for learning Poisson, but we will be using as counting a rare event. For those of you who are from finance later, or you learn some idea about stochastic process, then you will see Poisson is the way to model the most simplest memoryless stochastic process. Okay, you are trying to describe a random movement or random process, and Poisson is the simplest you can imagine in your mind. But anyway, we don't really need to worry about this because our class is not talking about Poisson process. So, but anyway, we were talking about Poisson distribution. So again, as we said, it is following from binomial. Okay, so we were also talking about a number of independent events occurring over a period of time. So you can imagine that the simplest thing in your imagination is you can consider over a period of time, okay? And you cut it into very, 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 very small pieces, right? And you can consider each single thing is a binomial trial, right? And event will happen with probability P, right? So then the whole thing, how many events will happen will become binomial, right? Right, the binomial trial. So it means that if I cut this as small as I want, and P is small enough, okay? And then I further cut it, right? So then this will become, when N is very big, okay? And P is very small, okay? Technically, it means N go to infinity and P go to 0, and NP is still positive, okay? And in that case, okay, the binomial distribution, okay? Remember the NX PX 1 minus P N minus X, you can prove, okay? I don't think we want to prove it. It's not difficult to solve, but we'll show you the other way around, but this one will, the limit, okay, will be equal to this one. So basically, if you take limit and go to infinity, okay, and then P go to 0, then you should be able to get this one, okay? So this one, I mean, it looks very weird, right? It's an E, it's an exponential, okay, to the power negative lambda, and lambda x, okay, and x factorial, okay? Turn out to be a limiting case for this guy, okay? And when the case is n go to infinity, p go to 0, that would be the thing, okay? And this is interesting thing is we will prove later, but that should turn out to be this. Instead of n and p, you only have one parameter, right? It's just one single number, lambda, and the different lambda will give different result, but what lambda turn out to be is both mean and variance, okay? That is sometime in technical term, you call it equidistant, or say equidispersion. But turn out to be interesting is mean equal to variance, right? Because remember, in the binomial is MP, NP, 1 minus P, right? So which means that the mean, right, is bigger than its variance, right? And NP, because P is less than 1, right? So that's why in the binomial, right? Sorry, in the binomial, the variance is the mean is bigger than variance, right? But in this case, we have the mean is equal to its variance, okay? It's a very interesting property. Sometimes you want it, sometimes you don't want to have it, but this is what it is. And of course, if you want to learn further, you will notice that there are other distributions that will give you the other thing, which is the mean is less than the variance, but we're not going to cover them. But if you learn further, that would be something would be useful for modeling, but we don't cover this in our basic class. If you want, you can study further. But the idea is the Poisson is a limiting case of binomial when n is very large and p is very small, and is used to, as we see p is very small and n is very large, is try to model very rare event, okay? And also do note that because we cut to infinity, so x can take, what kind of value we can take is any non-negative integer, so up to infinity, okay? So it's a 0, 1, up to very, very large number, okay? So that's a key difference between this and before. But because it's take a limiting case, then when you take the limit, you take infinity, then actually the math become much more simple, right? You can see we don't need to use the factorial, we don't use the combination, right? We change to E, okay? But we'll try to explain why there's a E there later. Any question before we continue? E is exponential, just a constant. It's 2.73. Da, 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 da. What's that is if you E is a constant, okay, and what's that is turn out to be is 1 plus 2 factorial plus 3 factorial, so on and so forth. And if you, another way to write is something like this, to the n. So turn out to be a very this whole this is a very it's a constant, you can trick it, but it says a number turn out to be like this. Is that okay? It's a natural, they call natural number. If you learn the mathematics, did I answer your question? So if you look at your calculator, that would be the EXP or E will be there. So it's not something that not very uncommon. I hope answer your question. So turn out to be this. Actually, the E is a very important thing in the mathematical calculation. But later you will see. Okay, but thanks for asking this question. But later you will see why this is equal to E. Actually, why we'll explain why this turned out to be E thing. Okay, you will later see. But E is a number. There's a constant. Okay. So here I try to show you what looks like a Poisson is somewhat, because it's, remember, it's a kind of binomial, right? So that's why you can see it's somewhat a bell shape, right? Because it's bell shaped stuff, right? So it's a rather a bell shape. But the thing here is more or less close to a smaller number, okay? And turn out to be, this is rather useful distribution to fit a lot of real world example. I mean, of course, if you try to look at a textbook or other place in the internet, you will see that so many applications there. I don't think I don't need to have too much explanation why this is true. Okay, but I hope what you remember is, for example, give you example. Okay, this is something that is commonly used in business application. Number of consumer for a restaurant, each hour follow Poisson, okay? Distribution with mean 5, okay? And what is the probability that exactly 2 customer arrive in next hour, okay? And what you do is directly apply the formula, right? Just E is a number, is 2.713, something like this. If you 2.713, almost like that, and raised to the power -5, because mean is 5, and 5, this lambda is 5 to the power 2, and 2 factorial. Okay, so this is the idea behind the Poisson. Okay, and this is commonly used. Okay, and I hope that's okay. And the mean is 5. Actually, it also means the variance is also 5. Okay, so this is x is 5. You see the lambda, because that's the same thing. Okay, so I'm trying to explain why, as I mentioned intuitively, that is Poisson. But before we do it, I quickly go over the why we can prove that is mean quickly, because the idea is rather similar to the binomial because they share the same thing. So quickly, expected value of x, right, is equal to x times the p of x, that's definition, right? And p of x is replaced by the definition, right? That's what the Poisson means, okay? And the next thing we're going to do is take, this is unrelated x, right? So constant term can be taken out, right? And x 0 times anything is 0, so it can start from 1. Okay? And the next part is x, right? This x and x factorial can be cancelled out, right? Because x factorial can be written as x times x minus 1 factorial, okay? So that's why the x eliminate. So that's why you have, it's the color, okay? And you give, it gives you to the x minus 1. And then the next thing what we do is to just a little bit trick. Here, lambda start from 1, right? So that's why I can take out 1 lambda, right? And then x minus 1. And this is well defined because start from 1, okay? And now do note that this guy, okay? Okay. X start from 1, right? But we can write y equal to x minus 1, the same trick, right? So that x is equal to y plus 1, okay? You start x counting from 0 to infinity, right? Y, sorry, x is from 1 to infinity, right? And that means y from 0 to infinity, the same thing, right? Because this is a interesting from infinity, right? The same thing. And you can replace x plus 1 by y. So this replaced by y, okay? But this one, again, is interesting thing. So this is what we call a definition of the e to the power lambda. So e is equal to, as I said, is 1 plus, so e to the power x equal to x. So this is 1 factorial, x squared, 2 factorial, okay? So this is one way to do x, okay? So that's why, again, e to the lambda, okay, will be e to the 0, right? 0 factorial plus e1, 1 factorial, e2, 2 factorial, and so on and so forth, which is this guy, okay? So that is a definition. And for those of you who didn't learn the advanced math, we don't, if you learn the advanced math in the DSE, you know it, but we don't really matter that, but this is just saying that this is the, sorry. So this is only the, to remember, okay? So, and this one become e to the power lambda. Okay, and the negative lambda and the positive lambda cancel out is 1, so that's why we have lambda left. Okay. So I hope that is fine. Any question? the next one is we will do a trick. Okay, that would be an interesting trick. Just let you know how this trick is arrived. So we want to calculate the second moment, right? Because variance of x is the second moment. Okay, this is called second moment minus the square of the mean. Okay, so that's why we know this is already lambda and square, lambda square. Okay, we need to show this guy. Okay, and this guy is not easy to show, but use another trick. We'll do this trick. Okay, because expected x squared is equal to x squared plus x, maybe minus x plus x. Okay, minus x plus x, right? So this is this guy. Okay, that's how we can derive the two, right? And we know this lambda. Okay, so we just need to figure out this one. Okay, and this guy turned out to be not difficult to see. So this, by definition, is x times x minus 1. Okay, I mean, I should be x0 infinity here. And the next part will be just the definition, right? This is this. Okay, and then here x start from 0, 0. Start from 1 is also 1, 0, right? So it's 1 minus 1. So you can start from 2, okay? And starting from 2 again, you can cancel out, right? The first two, okay? And then you can take this constant out, this here. You can take two of them out because you have start from, I can start from 2 because only from 2 is meaningful, right? And using the same trick, okay? This guy is again e to the power lambda, okay? And that's why they cancel out. That's left lambda square, okay? So we have lambda square plus lambda. So that is the main idea behind. Okay, so any question? Now this is the end of the proof. Okay, we have already shown this is lambda square plus lambda, and this lambda square. So that's why it's lambda. Okay, that's a little bit magic, but just let you know how they're being arrived. Of course, it's not terribly important, but just want you to show you how we get the solution. I mean, we try to prove something is easy, okay? We don't try to prove everything in this class, but it's important to know how you get those. Of course, I'm pretty sure you will forget. Neither do I remember everything, but just trying to see the reason behind to get those things. Okay. Before a break, I think it was a break, but very quickly give you the idea why this slide is not in your slide, because this is just there's two slides I talk about this. Some tricks talk about why how to explain the binomial and the Poisson very quickly. So don't worry about that. It's a very quick part. So if x is a binomial, right? What is px over x plus 1? Okay. Px will be nx, px, n minus x, right? This is the definition, right? X plus 1, same idea. X plus 1, x plus 1, x minus 1, right? Minus 1. And you cancel this out, right? Leave you p, right? And this is one more, so you cancel this out. That's just one left, right? So that's what I have here. And how do you get this one, right? It's n factorial x plus 1 factorial n minus x minus 1 factorial, right? The denominator will be n factorial x factorial n minus x factorial, right? And n cancel out, right? This is x plus 1, x factorial cancel out, you have this guy. Same idea, you have an extra thing, so cancel out, you have this here, okay? And you see from here, okay, let me clean this up. When you see from here, when n is large, p is small. When n is large, n minus x is very close to n because n is very large, right? So that's why this become n, right? And then p is very small, so 1 minus p is close to 1. Okay, so p is minus, so it's gone. So there's nothing here, right? And np is the mean. We call np is lambda. We just call np is lambda, say. Okay, we just denote. Okay, there's nothing here, but we say np is lambda. Okay, and that means next slide we will see px plus 1 can be written as lambda x plus 1 p of x. Okay, so this is something we need for the next slide. Okay, so this is how binomial variable x related to x plus 1. Okay, so from this we'll explain why the Poisson you see the E thing. Okay, so let's see the next slide quickly. Okay, so we have just said from the previous slide, we have p of x plus 1 and x, right, related by lambda over x plus 1. Okay, so we will do recursive substitution. Okay, px and px minus 1, okay, will be lambda x, right, because this is, we play this is x, right, this is x minus 1, and this will be x, right? And again, you can do this again, substitute this, right? This will be equal to p x minus 2 lambda x minus 1, okay? You multiply with this, will be lambda squared x minus 1, okay? And you repeat doing this again for x minus 2 up to 0, you will be lambda x times x factorial. Okay, because you can see 1, you have 1 here, 2 here, then 0, we have x minus 0 here, right? And then same idea, you say x factorial. Okay, and we know that the sum of all the things must be equal to 1. Okay, so, and you can replace this, okay, by p0 lambda x factorial. Okay, and this is constant, right? Can take it out, okay, right? You can take out this and divide the summation on the denominator, right? And the denominator is what? Okay, we have said this is actually e to the lambda. You invert it, is e to the negative lambda. Okay, and now that means p of x will be, this is e to the lambda. Okay, so that's why negative lambda, right? So that's why p of x is exponential to the e to the negative lambda x factorial. Okay, for those who ask me why this case, this is how we arrive the e. Okay, I mean this is notation, but turn out this is to compute this is very simple. That's e is just 2.713. Okay, so I guess it was a break of 5 minutes of the shorter break because of the we start late. So let's resume at 9:32. In the meantime, I answer any question that you might have here. Yes, break. It's a break until So I might open the podium to answer the question you may have right now. So feel free to ask me any question if you like to. So welcome back. Sorry for a short break. That's all. We start a little bit late due to the traffic condition. So I hope the traffic will be improving. The Eastern Tunnel. Let's see the last distribution we have. This again related to binomial. Actually, if you try to study a little bit further on this topic, you see a lot of basic probability related to binomial. Okay, and the reason why is because it is something related to a lot of sampling, right? Because this what happened in the real world is a lot of sampling, some trial, those kind of things repeat a lot of time. Okay, so the hypergeometric is much more related to those who are doing accounting, because I know there's a majority of the class is talking about accounting and the quality control auditing. Those are the things are related to the following distribution called hypergeometric distribution. Okay, what is said is you can imagine that a binomial, right, is a case where you sample with replacement. Okay, you are trying to what doing sample replacement is saying that okay, you are trying to let me share the screen. I hope you can hear me. Can you see the screen? CO factorial is 1 by definition. Yeah. So someone asked me when they calculate the CO factorial, by definition 1. Okay, 1 and 1 factorial is 1, and okay, there's something very funny, but this is turned out to be this is the way we define this thing works. So that's why this is standard definition. And the thing is like, we talk about this quality control and sampling, right? Suppose we have some object here, okay? Suppose the 5 objects here, right? This is a good object, good object, good object, good object. Last one is bad object, right? We know there's 4 good objects and 1 bad objects, right? And then if you try to take out an object from there, okay? And what is the probability that you take out the bad object, okay, right? Then the probability you randomly draw, this is 1/5, right? And or you can say 0.2, right? And if you take it out an object and check if it's good or not, right? And you put it back, okay? You replay it, put it back, and then you do it many times, right? And ask how many times you got a bad object, okay? Then that is a binomial distribution, right? Because every time the probability success, which is taking the bad object, is 0.2, okay? You take it out and put it back, okay? And that is a binomial, okay? And you may ask, hey, when we do audit, why do we put it back, right? But when you face a large quantity of stocks, right, and turn out to be there's no different when you model it as put it back or not. Okay, later you will see whether you take an object out and check whether it's good or not and put it back. There's no difference between if a lot of object. There's not much different when you put it back or not. Okay, and in that case, binomial is a good way to model it. With large object, right, and you figure out how many are bad, right, and if there's a lot of objects, then whether you put it back or not doesn't really matter. Okay, but sometimes when you go to a warehouse which has only few stocks, okay, and you have some probability how bad they are, and in that case you really cannot put it back, right, because it's very not few number of them, right. Then you want to see how frequent that you will get the bad thing, right. Suppose there's only 5 objects, right. Suppose you want to take yes. The record, the lecture is record. Yes, don't worry about that. In case you miss it. And also do remember that the whole lecture is pre-recorded. So even if you don't like what we taught in the class, they're already recorded for each part. So it's pre-recorded already. And also we record the real-time thing. Is that okay, Charlie? Yeah, so of course, in case you still have question, then we can talk about next class, because next class we will be, just remind you, we will have a quiz on up to the discrete random variable. So you know better. Again, don't worry about that. It will be not really graded, just by attendance. Okay. Yeah, same style. Just multiple choice, I guess. It will be multiple choice with 10 or 12 questions. Just so this to test whether you understand or not. Again, it's about attendance. Okay, just you do it and then you're done. I guess we'll be doing. I think we'll continue to do it through the Blackboard. I think Blackboard is okay, I guess, right? Otherwise, we can do uReply, but I think the Blackboard is okay. Unless you have some concern about Blackboard or uReply, otherwise I will just click the Blackboard, because I think it's might be I don't know. It's harder to use Blackboard, but I think it's better for you to use Blackboard because many of you know Blackboard. I don't know. Let me know if you have any preference. So go back to the hypergeometric one. Is saying that you try to take objects sampling without replacement, right? Say again, go back to here, right? And we have 5 objects. 4 of them are good and 1 of them bad, right? And if you just take out 1 object, right, what's probability you pick out the defective item, right, is 0.2, right? But what happens if you take 2 objects? Okay, what's probability you take the bad objects? Okay, how likely you would get the bad object? Okay, so that is the question. Or more generally, suppose you have more interesting, you have 6 elements, out of them 2 are bad. Okay, so how likely you're going to get 1 bad object or 2 bad objects, right? That is very important, right? Because, or as important in engineering, right? Usually the plane, right? Commercial plane, you have 4 engines, right? The big one. And usually if you failure of 1 or 2 engine doesn't really matter, but failure of the 3 engine or more will have problem, right? So you have to calculate the probability that what those things happen, right? Then you can see how many engine you need, those kind of idea, right? Some of a backup system. And same as idea, using hypergeometric can give you idea quality control, right? Suppose there's a the machine is defective, right? Or it's not possible to produce perfect every time, right? Then you need to check how likely they are, how is the function, or how, whether you need to check whether the box of the object are good or not. This is something very common. Okay, so let me get into the Hypergen measure, then you appreciate the motivating example we have. Okay, so n is number of time, or you can say n is the total number of element. Okay, total number element. Okay, you can say it's total number of number item. Sorry, it's title for item, and we'll call A of them success. Okay, so in that case, we want to pick up the effective product, right? So this, in this case, n is 6, right? And A is 2, because we want to pick up the effective product. So when we pick up the effective product, successful. Okay, and x, okay, the random variable x is small n. N is the sample. Okay, we are drawing how many sample we have. Okay, n is a sample. Okay, depending how many sample we want to draw. Okay, we may pick up one element, one object there, or 3 or 4. It depends. Okay, and for what we need, n is less than a. Okay, we are not drawing more than a, because the reason why, if we draw more than a, then we'll always have a. Anyway, this is the definition. Anyway, so what it means is, suppose we have many objects, say to be this way, with n object, okay, and A of them are success. So you can imagine A, we're using the notation here, cross. So there are a lot of cross here, okay, and there are a lot of tick here. They got n minus a, okay, n minus a, right? And we try to sample. We try to pick up n samples. So n samples, the n samples, okay. And we are asking how many x of them. So we're asking how many x of them belong to the A. Okay, let me repeat again. What do you mean by here is, we have n objects, n number of items, okay? And out of them, A items we consider success of good items, okay? Or whatever we consider success, okay? Can be whatever, something we care. And n minus a, we don't really care. We don't call it success, okay? And then now this is the background. Now we're trying to sample. We take out n element, okay? N element over there. And this element we assume to be less than a, okay? And this n element, we're asking, this n element, we sample, take out one item, an item, an item. How many of them are success? Okay, we're calculating probability. Okay, so that's the idea. So here we have P equal X is n small n, big N, and A. Okay, and the probability turned out to be, okay, the denominator, okay, is how many ways you pick up n object, right? Because we don't really care how many ways you do, is n object, how many ways you can pick up is small n. Okay, that's why the denominator is n combinations n. Okay, NCN is because n object, right? You can imagine that is the ball 1 up to n, right? You try to draw small n out, so that's why it's NCN. Is that clear for the first denominator? Is that okay for denominator? Yes. And the numerator, okay? So first we need to draw, okay? What's the probability about is you have X of success, okay? X of success, okay? And N minus X of fail. So that's the idea, okay? And so first, how you draw success, right? And you will need from A element, you draw X, right? So that's why it's ACX, okay? And then how many element is failure, right? N minus A failure. How many you draw? N minus X. So that's why this is the way the probability. Is it okay? Good. So it's very commonly used to quality control. Okay. As I said before, so for those of you who learn audit and you will or accounting, then you will be something very useful. Of course, binomial is also very useful. And later you will see that it's very similar to binomial. So try to see how we relate to binomial. So the mean we will show immediately is NA over N. Okay, what's this? So look again. A over N is what? It's the proportion of the successful item, right? So in terms of binomial, this actually is P, right? So that's why it's NP, okay? And the difference of this is you are now not drawing replacement, right? But you draw it without replacement. Sorry, you draw it now, you draw it without replacement, right? That's true. So that's why looks different, but in terms of mean, the same thing. It's still NP. So it's very interesting, right? Because binomial is NP, but hypergeometric is also NP. Okay. So when you estimate mean, actually there's no difference. Actually, you can see that from a general thing is that the mean, when you take things with replacement or without replacement, turn out to be the expectation is there's no difference. Okay. But here comes the main difference is the variance, right? The variance should be NP times 1 minus P, right? This is NP. Actually, this is N, this is P. This is 1 minus P. Why 1 minus P? Because P is NA, 1 minus P is 1 minus P, right? This is 1 minus P. We can see this M1 minus P. And this is the part that I said when the N is super big, there's no difference, right? You can see if N is very big, this is close to 1. Okay, when the big N is very big, okay, this is close to 1. Okay, so you can see from here that when you try to sample the thing is a real huge quantity. Whether you model it as a sample with replacement or without replacement, that's not really that matter. But in another case, this is not the case. Okay. The reason why this, you can see this as a fraction, right? N minus 1, right? This is less than 1, right? You can easily see that the variance is smaller because you try to draw things and the thing get fewer and fewer, right? So the variation would reduce, right? Compared to the case we keep drawing, replacing things. Did I make myself clear? Of course, we go to example and try to prove that this is the formula behind, but I hope that's okay. Probably you think that it's a little bit, the foundation is not very strong, what you learn here, but because of, we don't give you the assignment yet, but when you do the assignment, then you will see, you will learn more. Of course, the the next class, we'll be working on the quiz, then you will know a little bit more. Hopefully you do some revision. But anything before we continue? Of course, in the quiz, we'll probably just ask you how to apply this mean, this variance, how to apply this formula, okay? Not the proof, because it's multiple choice style, just application. Just would be somewhat of variant that you see from the example that the green thing, something like the green example, somewhat like this kind of style question is something that you want to apply, and this is something we need to learn. Okay, any question? Is that okay? If no, then we continue. Here I have another example to show you how this thing looks like, right? For the red one will be n equal to 4, n is 10, a is 5, right? This is actually p is equal to 1/2, right? So that's why it's very similar, right, to the binomial, right? N for p 1/2, right? And this one, right, p will be equal to 0.75, right? Somewhat like skewed binomial, right? So as we said, this is very similar binomial, but when n is getting bigger, then you don't see too much difference. But it will be important when you have a number of n is small. But anyway, let's say example, okay? Something, as we said, the warehouse, okay? So now with warehouse, we have 30 computers and 4 of them are defective, okay? And now the question is, what is the probability that 2 out of 4 of them, sorry, you take 6 sample, what is probably 2 of them are defective, okay? And before we solve this question, you may ask why we care about this, okay? We do not cover this, but this will be covered in more advanced application, okay? But that is actually not difficult to appreciate why we need this, and not difficult to understand why what we'll be doing for more advanced application, okay? You go to a warehouse, right? You try to check, okay? 30 of them, you have some conjecture. You think that, okay, 30%, 30 of them, 4 of them are defective, right? So what's the defective rate? Is 4 over 30, right? Right, so 4 over 30 equal to, let me calculate, 4 over 30, okay, is it's a 30% defective rate, okay? Then this is in your mind, okay? You go to the warehouse, you check, okay? Turn out that this is 2 of them are actually defective, okay? You take out 6 sample, okay? And then you want to say, oh, how likely is this is true, right? The 30%, right? Okay? Turn out to be this probability, okay? We tell this, okay? And you want to say, yeah, is it very likely or not, right? If this is not very likely, you think, I don't know whether you think it's likely or not, then you try to query, okay? Why that's the case happening, right? Just to go back, the idea is you would go to the warehouse, right? Actually, you don't know how many items are defective, right? You just pick out, say, 6 sample, okay? You try to see, okay, out of 6 sample, you have 2 defective, okay? You try to go back and guess overall how many of them defective, okay? You're reversing the question, okay? But using some of technique you learn in the second of the class or some variation, we are reversing, okay? So just to repeat, actually what we're doing is, right? Here is where we will, okay? Okay, we have some assumption on, some description on the world, right? So how many percentage are defective? Okay. And then we're calculating the, say, the hypothetical case, hypothetical probability, right? Say, oh, out of 6 sample, 2 of defective, right? 2 out of 4. What's probability of this? Okay, and we know the probability, say, 4 out of 30, right? This is what happened, right? This is given here, right? You try to, the viewer is this, right? We're trying to calculate this number, okay? And later, if actually you do is reverse, okay? Is suppose you take out sample of 6, okay? So not sample of 4, but sample of 6, right? You figure out, and this actually happened. You are trying to guess at the end of the day, what should be this number, okay? And you try to say, why you got to guess this number? Because this number is what your client usually tell you, right? Oh, they tell you, oh, in the inventory, oh, this is good, this is bad, right? And then what you do is try to randomly open some boxes, figure out, okay, this satisfy what they said, this doesn't satisfy, and try to judge whether that guy is doing right or wrong, right? If turn out to be, if not that right, then you pick up more box, right? So that is what you do in the audit, right? That is something very common. Is that clear why we are doing this? But before we can do the reverse way, we have to understand how to calculate this. But that is the main idea why we do a lot of sampling so far. The same idea about the other application, right? Suppose you try to check how many people out of the sample of 6 have disease, right? We can infer back how many people in the population have certain kind of rare disease. So that's usually how the medical profession judge what's the percentage of people have, say, certain type of cancer, right? They do a sample and to try to infer what happened in the real world. But at the moment, we are trying to do this first. Otherwise, if you don't know how to, from this direction, we cannot infer backward. But the second half of this class, I think that after 1 or 2 more weeks, we'll go back to answer this question, right? This is called the descriptive statistics, right? And go back is the inferral statistics. But anyway, let's continue on this calculation, okay? But any question about the framework that we are working on? Why we care all this kind of thing? Same as the Poisson order thing, right? We're trying to guess, look at how many people are coming to the coffee shop, right? And come up with the idea of the Poisson, okay? And guess what happened in the underlying distribution, right? And then we can see, say, how many chair we need, how many labor we want, right? Because to guess how many people we need, right? So that is actually probably behind the mind of the management of Cathay Pacific, right? They decide how many people to keep, how many pilot to keep, those kind of ideas. Is that clear? Is that okay? So here, go back to this question. Now we have n is 30 because this is number of object, and defective is something we care cause success. Actually, A is 4. Okay, and the sample of 6 is n is 6, and we have x is equal to 2. So that's why it's n and a, right? So this is ACX, right? N minus a, n minus x. This is n, okay? And then you compute, then this is 0.1511. Is that okay? So you will be working this kind of question, of course, a little bit more complicated here and there, but this kind of style of question in your upcoming quiz. I hope you can revise a little bit before you come on first day, okay? Because that would be testing whether you understand all the problems or not. Of course, although we just test this, you will also need to use the knowledge about the previous topic, right? Say, suppose I ask you, what is the probability that less than 2, right? You have to calculate probability x equal to 1 plus probability x equal to 0, right? Plus probability x equal to 2, right? Would be, if I ask you, what is the probability that is at most 2 defective item of 6 objects, then would be, you have to calculate all this, okay? Something that the previous topics knowledge will be assumed. Is there any question? Okay, if no, then we will be doing the proof. Okay, so in the proof. Okay. Again, that will be actually very similar idea, okay, to the binomial, because as I said, everything is a similar binomial. So the proof is also a similar binomial. Okay. We will progress a little bit slowly, but you can see the math is not very complicated. First, this is summation xpx, right? And this px is this guy. Okay. And now we do some tricks here. We'll say, we'll show you this. Maybe there's other color. Okay. This guy is same as this guy. Okay. So actually, this is just probably we're the same trick already. Say what is ACX is A factorial, X factorial, X A you cannot see my screen. Yeah, I share my screen, but I share it. Can anyone see my screen? Okay, someone can't see it. Maybe Kai-Chung, can you see it? No. Can you share again? Is that okay? Okay. So A minus X factorial, okay? And you can take A out X out, that will become A over X, A minus 1 factorial, X minus 1 factorial, A minus X factorial. And this one turn out to be A minus 1, X minus 1, and A over X, okay? So that means that AX can be written as A over X, A minus 1, X minus 1, okay? And denominator okay? N, right, will be n over n, n minus 1, n minus 1, okay? So that's why the denominator is this one, okay? And numerator, that's x, and the x cancel out, that's why it's a. Is that clear how we arrive the second step? Is that okay? Is that okay? Okay. Is that clear? So you take n over n out, okay? Basically, n is going to be out, a going out, that's why you left this guy, okay? So actually, we already know this is the goal we want to prove, okay? So this must be 1, okay? How to prove it 1? It must be sum of all the probability of certain thing, right? So that's the same trick we use for Poisson or binomial. So we already using always the same trick, okay? So we want to prove this is guy is 1, okay? So that's the goal. So let's see how we can do it. The trick is, again, we will be changing the index, right? X summing to 1 up to n, we try to change y, sum to 0 up to n minus 1, right? In that case, y is x minus 1, okay? Or x is equal to y plus 1, okay? So we change x to y, okay, from 0 to n minus 1, and y minus 1 become a. So y minus 1 become y, okay? And this x is y plus 1, okay? Okay, so in that case, you have here, right? And this guy is indeed 1. The reason why this actually is a hypergeometric, right? With a become a minus 1, n become n minus 1, small n become n minus 1, right? The same idea here, okay? And this guy is 1, okay? Because sum of all the probability in the sample space, okay? So that's why you have n times a over n. Is that clear for this one? Okay, but you can see all the trick are the same because always the same trick, right? Just take things out, sum of them to 1, and that's how you prove it, okay? So that's why we repeat several times here because they're really the same thing. Is that okay? Now, if okay, can I have you say okay in the chat? Okay. Of course, as I said, it's not terribly important to remember the proof, right? But it's good always to know how you prove things. I mean, of course, you don't need to remember every step, but you will understand the whole logic of the proof. So here we will do the same trick here, okay? Instead of proving this, right? We'll do another cut. We'll prove this first, okay? And because this is equal to this one, okay? We know the mean already, okay? You know this guy, right? Because this guy. And at the end, we want the variance of x, right? Because this is equal to this minus this guy, okay? So that is the key here, what we are doing. Now, let's do the calculation, okay? That is not terribly difficult. This, okay, by definition is this time the property x, okay? And we do the same trick, okay? I just do it a little bit quicker here. Here is n over NCN, okay? The first step will be n over n minus 1. Sorry, this is and n minus 1. But we can do the trick again. It become n times n minus 1. N times n minus 1 will be n minus 2, n minus 2. Okay, so that's how the denominator comes in. Okay, fully from n over n. Okay, the same trick to ax. Okay, ax you can have ax, acx will be a minus 1 x minus 1 will be a minus 2 x minus 2. Okay, and x minus 1 will cancel, so that's why you have a minus 1. Is that clear for this? And of course, x come from 0, you can start from 2. There's no difference. Now, the same trick again. These are the constant unrelated to x, right? You can take it all out. Okay, you have this, this, right, and this. Okay, and denominator will remain denominator, and the rest. Okay. Now, you may ask what this is, right? Using the same trick, this will be 1. Why? This is just saying that you have same idea, right? You have n minus 2 objects. You pick out x object, right? You will be taking out of n minus 2 object and a minus 2, okay? This is the Poisson hypergeometric with parameter n over 2, n minus 2, a minus 2, and n minus 2, okay? This is, some of them are all 1, okay? In that case, this is this quantity, right? That means the second moment, right, will be this guy, right? This is x. Now here comes the last part. I hope that is okay, because actually we're using the same trick again, and again. So that's why we cover this part. So not all the proof we are working on, but try to show you this because they're very similar. So that's why this is good to show you why we are doing that trick. Okay, just a little bit. Okay, just bear with me slightly, the math. Okay, so this is we prove. Okay, this is the mean. Right, this is NP, right? If you remember. Okay, and then what we do is just take the NA out, NA over N, right? So NA over N is 1. This we left N over the square with N over N, and take out N over N will be just left this guy. Okay, and when you do a fraction, we use the primary school method, right? Make the common denominator, right? So we have N1, N, A, right? This is, we have N minus 1, N, right? And we can rewrite it. I mean, probably I just left you to do from this part, and turn out to be, you can rewrite it with this guy, okay? I'm not going to tell you the detail of, I mean, you can do it by yourself for this part. And turn out to be, again, let's repeat why this is important. This is NP, this is 1 minus P, right? And this is what we call, sometimes we call the finite sample correction, right? Because when n goes to infinity, right? This guy is 1, right? And over n minus 1 close to 1. Okay, so that means that when you have a large sample, you can use binomial to save your calculation, right? So we don't prove it, but you would see when you do actual practice, right? Hypergeometric is complicated, right? So sometimes you can use binomial to save your life. Okay, but of course now you have computer, so you don't really need that. But in the old days that would be very useful. Okay, I get this pretty much. I want to talk today, and because we already finished this topic, I don't think we should continue. We should stop here. Although we still have some time, but the rest will be because we have a quiz anyway, so that's why I think I should stop to open the time for you to ask any question.
Good morning, Professor Cole.
Yes.
I just joined last class and I'm trying to catch up really, but yeah, I guess I'm doing good. But in terms of what I missed, I think I missed 2 quizzes, right?
If you just join the class, you don't really worry about that. You will be proportional to after you join.
Okay, so
I think the quiz 2 is already there. You can check it back. I think I put the question on the and answer on the black box, so you can look at it.
Okay, maybe I can shoot you an email.
Okay, but it's, yeah, you can shoot
it. 3 is next week, right?
No, the quiz will be on this Thursday.
This Thursday.
The quiz is just attendance purpose, so don't worry about it.
Okay, so we have to complete the quiz this Thursday.
Just finish the quiz, and that you know how well you're doing, and that's the only purpose.
This is quiz what? Quiz 3.
Quiz 3. Yeah.
Quiz 3. Okay, so and we have an upcoming that is due on October 16th, and that is the homework one.
Yeah.
Okay, sure. How about the group project?
Yeah. Wait a second. I'll just say goodbye to. So if you group project will be, I think we would be. I would be. Maybe I'll talk about this in the next class. That would be better. I think.
Okay, so I didn't miss it.
Yeah, didn't miss it. I will talk about next class because I think until 2 more days there's a add job will end, so I can talk about those things.
Okay, sure. So once I complete quiz 3, I will just, should I send an email to you, or it will be automatically?
You will be there if you're in class. So we will go to class. Next class at the beginning we'll have a quiz.
Okay, sure. Okay. So it will be in class, the quiz.
Yes. You'll be doing it in class. Yeah.
Okay, sure.
We discuss the solution and all the thing, and it's a way to learn. Yeah.
But even if I got some answers wrong, I don't need to worry, right?
Yeah, miss the attendance.
Yeah. Okay, sure. Okay. Thank you. So I guess I'm still on track. I haven't missed anything major.
No, nothing. Yeah, okay. Just remember the homework to be submitted on 16. Yeah.
Okay, thank you very much, and I'll see you next time. Thank you.
I see you on first.
Thank you. Goodbye.
Goodbye. So bye. Thank you. I see you on Thursday. For those who are just waiting. Sorry for that. I thought I should have said goodbye. Thank you. I just remain to answer the question if you want to. I mean, many of you are busy in life, so just we do meet on next class or with a fun quiz. So take your time to do some revision. I think that will be helpful. But as again, no pressure because it's attendance based.